me share my screen. Are you able to see my screen?
Yes, Professor.
Yeah. So this lecture forms a part of the introduction to predictive analytics, I can say. So why math is required? Sorry, there is a. Can somebody mute, please? So why did we learn mathematics? So
Sorry, Professor.
yeah. Why did we learn Excel functions? Because to prepare data and all. So why mathematical modeling is important, and why statistics? So all bits and pieces of puzzle why we learned. So it gave an idea to the regression or a modeling framework to our problem. So like as students ourselves, like in our high school or in our plus two or in colleges and all, we did some of the other projects. It might be a drawing project, it might be some model, science models, or environmental model or something like that. So using cardboard and those kind of things and all we did. We tried to replicate what was in the actual scenario. That's what we did it. So in that kind of a scenario, this helps. This kind of modeling, why we do this modeling, this helps. So we learned it all step by step, and whatever we learned. So this regression will tell you an amalgamation of. So for business students, exclusively for basic classes and all, we teach only simple linear regression, which can be extended to multiple and all. Of course, in our mathematics class, we saw polynomial regression, quadratic regression. Of course, those are, to have that kind of data, you are expected to get that kind of answer. So you need to model it like that. So those are things which we learn. Today, in this scenario, we learn simple linear regression. So here, what is a response variable? What are the predictors to it? With a very basic example, we'll try to learn it. Let's see. So how to use simple regression to predict the value of a dependent variable based on an independent variable. So we learned the equation. So I taught you about what will be to the left of an equation. To have an equal sign to the right of an equation, what of that formula, what will be there. So these are some things which we learn. So it is not a waste or something like that. It is not that simply we learn. These are all connecting dots to it. That's why we learn this thing so that it will be easier for you, do these things in real world, real life projects and all. That's an idea. So meaning of the regression coefficient T0 and T1 to make inferences about the slope and the correlation coefficient. So yesterday, that's why I ended my testing till correlation. So that is very much important here. So after correlation, we learn regression. To estimate mean value, predict individual values. The same concepts can be extended to multiple regression. So this is what we will learn. So this chapter is also there in the textbook. So with other examples and all, of course, I use a part of my slides from my predictive analytics class so that it so to connect the dots and all. So I think I have shared all this thing to you via WhatsApp. So you can download it. I have shared the data sets also. You can use it. So regression analysis is used to predict the value of dependent variable based on the value of at least one independent variable. Explain the impact of changes in an independent variable on the dependent variable. So what is the dependent variable? That we have to understand. The variable we wish to predict or explain. So that will be to the left side. Independent variable is the variable used to predict or explain the dependent variable. That will be the right side. So that is how balance this thing. I think I had shared this if I remember right. So this is the slope-intercept form. This is basically high school mathematics. So we all learned it. I learned it. So I think almost I can say about 45 years back. So you people also might have learned it in various, say something, some might have learned 20 years, 15 years, or whatever, even 2, 3, what, 5 years or 10 years back. So you might have learned this thing. So this is the high school mathematics. So everybody was taught this thing. Even I was taught this thing. So purposefully it has been given here. So we recall line of best fit, slope intercept. So I had some y, I had x. So I calculated an equation, I got the answer. So we used to plot this thing. I think in our 9th standard or 10th standard examinations, we had this thing. So they used to tell like it was a 5-mark question or a 10-mark question we need to prepare and all. So everybody did this thing and we got some marks for it. So this what we had learned is basically regression. I think in our maths class we also saw this. So in our simple linear regression model, we only have one independent variable. So to the right, it is always denoted by x. Why this x and y has come is that because all the mathematics people started denoting these things like x and y. You can have it a, b, c also, no problem, no issues. But mathematically, people can relate to x and y. So over the years and all, people can relate. That's all. Nothing wrong if you use m, n, p, q, whatever it is. That's fine. But yes, x is used. Relationship between x and y is described by a linear function. Changes in y are assumed to be related to changes in x. That's what we understand about this model. So how are the linear relationships? We plotted some of the things in our class in mathematics. So of course, we didn't give emphasis to this thing. But yes, so when we had a linear relationship, we always got a linear regression form. When it had a nonlinear relationship, we fitted a polynomial curve and a quadratic curve or whatever it is. So, so it is based in 4 quadrants. So the first quadrant is a nonlinear relationship. It will be like in hill, something like a normal curve kind of a thing, where it will be denoted in the way it is. The second quadrant, it is a linear relationship and it is somewhat positive relationship, we call it. So third quadrant is a negative relationship, but it is linear. Please remember that. So fourth quadrant is also nonlinear relationship. So it is some kind of an exponential or something like that. So that form it assumes. So that's the way we have this thing. So theoretically, how this graphs came about. So I think I have told like statistics has been there for almost 120 years, 130 years now. So people have noticed that this is the kind of linear relationships you can expect. So this all textbooks everywhere you have this kind of diagram there. So at a general sense, when you plot a scatter plot between two variables x and y, you get one of these things. So in that thing, if I put some kind of a more impact to our understanding, a strong relationship is shown in figures quadrant 2 and quadrant 3. A weak relationship is denoted in quadrant 1 and quadrant 3. So this is how we get it. So strong means like the line of best wherever is the dark line there, all the points center around. So the best example is like as human beings, we live on Earth. So it has a gravitational force. Everybody is drawn towards that gravity here. So when we go to moon, so it is like a weak relationship. So we try to float. So that's how we can understand this kind of relationship. So when there is no relationship, we get something like this. As I told you, this is not expected somewhere in business or some things and all. Maybe sometimes in scientific experiments or very in outlier form, some engineering relationships, we can expect this kind of graphs. So coming back to the Greek form of this model, so I have a dependent variable y, which will be to the left. So it has a, it is spoken as B is whatever we know is known as a beta in Greek terminology. So yi is beta naught plus beta 1 xi plus epsilon. So very early in our statistics class. So statistics is a stochastic sense where error is very, very important. If you don't have error, you cannot solve problems. Definitely, we cannot expect 100% thing. So when there is no error, that is known as deterministic problem. It's really studied in prescriptive analysis. So beta naught plus beta 1 xi is the linear component. Random error is the other component. So usually the equation is written like this. So y is the population intercept. The beta 1 is the slope coefficient. 1 is the independent variable xi. Random error term is denoted by epsilon here. If we convert this thing to a form, so it becomes something. It is like y is equal to a plus bx kind of a thing. So in a regular basis, we try to use it. So where does it fall? How does it fall? This is the thing which we have to understand graphically. So we had an option in Excel. So it plotted something. Insert a line of best fit, it will fit and give it up. That's fine. But where, why, and all, you have to interpret. So in the data which we have done in that example of that day in the mathematics class, so we had something, we fitted a line of best fit, and we had values which was above that line of best fit and below the line of best fit. So those are the actual points. And what is the best line of fit is that the red line is it's denoted by that thing. So intercept is the red line will meet the y line. So that is known as from 0 to that intersection is known as the intercept or beta naught. So what is epsilon? Random error. So the point probably if it falls on the red line, the blue line, the difference is epsilon. So that is what we are trying to minimize. So if you see the point, one of the blue points is on the line itself, here and here. So they have actually that points are very good. So they tend to towards the gravity. This point, one below the line here, and this one, and this one, and all are very much not an outlier. It's away from gravity, we can say. So this line, the line of best fit, can be called as gravity. So the slope coefficient is known as beta 1. So this is what is denoted by it. So it is not rocket science, nothing magic will happen. Everything is in front of your eyes. That is how we trying to do it. So for past 120, 150 years and all, it has evolved in maths. Of course, it has been adapted to statistics in this way, where we do this modeling. It's a mathematical model only. If you do inference on it, that is known as basically statistical analysis, and we call this as a simple linear regression model. So that's how all things mix, the cocktail mixed here. So people may not understand this. For a common man, this is very much not of much use, and only mathematicians, statisticians, so somebody who are very much strong in maths will understand all this funny equations. I have to convert into a business language. Even though it's maths here, I'll show you how that can be converted to a purely business equation also. But at least for a theoretical understanding for a business student and all, it is better to understand in this way. So what I get a yi to the left of my equation is known as a y hat, we call it, or it is an estimated line. So using the equation, I can predict the future also, or I can predict whatever the points which I had for y also. That is always known as an estimate. So beta naught is the regression intercept which we saw. So this beta naught becomes B0 in our case. B1 is the estimate of the regression slope, which is shown there, and xi the value of the observation. So here I have got two columns of data. One is y, one is x. Using a magical formula like this, I come to find out a equation for this thing, which we already done, but we'll go more in a scientific way, understand how exactly to calculate. So we get an estimate of this thing, and we get this equation. So what is this B0 in this thing? B0 is the estimated average value of y when the value of x is 0. That is true. So if I get values of x is equal to 0 here, so B1 also becomes 0, B0 becomes an average. So whatever y I can estimate is an average value. B1 is the estimated change in the average value of y as a result of 1 unit increase in x. Can be as simple as 1 unit. The unit is something like dimensionless here. So it can be centimeter also, it can be inches also, it can be rupees also, it can be dollar value also, whatever it is. So we'll use an example to understand all these things, why, how, and all. So B0, estimated average value, B1 is the estimated change. That's how we tend to understand in a very, very simple way. So how to put this in Excel also has an algorithm inside. All the magic happens using this least squares method. So we have to formulate this mathematical statistics people will know what is least squares method. For the sake of completion, I have given you. You need not know this thing, but what exactly happens inside I have shown you here. And how to code this in Excel or R, Python and all, that they have done it already, but for your understanding, we use numerical methods. I think people who have studied engineering and all might know that you had a paper on numerical analysis and you had some methods which you learned like Newton-Raphson method, Runge-Kutta. So it is all coded in that form. So any mathematical equation can be converted to its numerical form using Newton-Raphson or something. The same can be translated to a code, a computer code. In Excel also, we use a GUI, we get the answers like click of a button, but behind this is the thing which it works. So as I told you, it requires some formula and all. So how to calculate all these things are given here. So B1 is SSXY divided by SSX. B0 is Y bar minus B1 X bar and all. I'll show you through an example. What is that thing? Yes, this is the one. So I have two things, X and Y. Something disturbing here. Move here. Yeah. One is direct labor hours, other is factory overhead. So for this data, I calculate x into y and x square. I take sum of all those things. And from the table, I get certain information. I get summation x square, x bar means we have learned it. So summation x is something like we sum the values, whatever it is there, substituting these values in the formula for b. I have to find out somehow the b, right? So I get this thing. So b is that b1 here. I get a value of 0.56 here. And A is that B0, we can say that. So Y bar minus BX bar is there. And if I impute all, because I have calculated B, and I get a value of B. So whenever you put the data, here I have only one Y, one X. Only one Y is there. There might be X1, X2, X3, X4 also. The same kind of formula will be there, but the formula becomes complex. We cannot handle it using hand calculations or even calculator and all. So we need to resort to using an Excel or some kind of programming language. So the equation I get at the end is like I had a 1y, 1x. So my equation becomes y is 10, y hat is 10.58 plus 0.56 x. This is the equation. So if you remember that our class on fitting the line of best fit. So there we had this kind of equation where we had 1x, 1y. The same thing through calculations, if you do it, you can do it like. And begin. So for anything, so let it be 1 million rows of y and 1 million rows of x. Same formula works. Of course, Excel cannot handle it. You need to resort to some very big server kind of systems, but it will calculate for you. You can get the answer within seconds. So I got the equation. So I don't know why it's not moving. So I need to find out this equation. So for the very simple problem, this I have got it. Similarly, if I go a few slides back also, in our high school also, we would have got this thing. We calculated this thing, same thing which we have done it. The formula behind that is, so this was taught to us. So this is the thing, purposefully like that. It's a screenshot. I have copied it from the web and put it for a simple understanding. So let me stop here for a moment. So I welcome any questions if you have it. So else I'll move to the solving in Excel and trying to interpret it. Any questions, any doubts? Are you able to understand what I'm trying to tell?
This one we got because some day back on managerial economics we learned direct labor, factory overhead.
Okay. Yes, good. You can connect to the example. Yes, definitely. Yes, it is a problem from managerial economics. Of course. So there it would have been solved, or even managerial economics people do use this kind of regression techniques for some things at some point of time. May not be always, but they definitely use it. But this is how we can. So it can be anything. Example can be from A to Z of whatever domains you may say. So A of anthropology, Z of zoology, anybody can use it. The same formula will. Only thing, people who know this thing are working in that area can connect to the numbers there. So as you told, people in managerial economics will very quickly relate to it. For me also, it's a challenge. For somebody else also, somebody coming from a different background, say, for example, biology, learning statistics, if I show this example, he or she will really say that Professor Amarnath is teaching nonsense. But that's not the case. Please remember, domain is very much important. Formula is same thing, you will do it anywhere. So we have to understand this example now. So how, why, and all we'll understand. So our example is, I have one Y, one X case only. So a real estate agent wishes to examine the relationship between the selling price of a home and its size measured in square feet. So he has only 10 records. So dependent variable is house price in thousands of dollars. So whatever you see, the Excel file which I have shared has some numbers like 325, 234 and all. So how you should understand is like 234 into 1000 you have to multiply. So that's the answer. Purposefully, to balance the square feet and the house price, I have diminished the value of this thing. But while interpretation, we have to get back to that number. So this is the data I have. So let's also solve this thing. So if I say 245 into 1000. That's what is the actual number. So it will be 245. So it is $245,000. I don't. They don't say 2 lakh and all. They say mention something like that. So square feet for 1,400 square feet of house or land or whatever it is, it costs $2,45,000. So that's how we need to understand this problem. So if I plot this thing, so scatter plot, it looks something like this. So when you see this thing, it looks somewhat positively correlated in terms of the correlation. So we'll try to fit a model to it. So why the model we have to fit? So if any new person comes, So what the real estate agent will do, like, you just put the value of the X beta naught and B1 will be readily available. He'll put like for now example, he has data of some historical records, 1400 something like that. So if a new house comes up for sale with him, so which is about 3000 square feet, for example. So the equation is ready with him. He'll put 3000, B0, B1 will be ready, and he'll have the price of Y. So at that point of time, like Amarnath would go to that real estate buyer if he's looking for some 3000 square feet of apartment. So the bargaining starts. So he will try to bargain. So that's how things work. So historically also, scientifically also, historically he should have data. He has modeled, maybe real estate agent may not model it. Probably somebody like a data analyst would have modeled and kept this ready. So we may not see this thing. You will be sitting on the other side of his table. He has a computer and all. Even he will not have regression and all. He will have a application ready with him. You just put the number, he'll get an answer to it. So he'll quote a price. Price negotiations happen and all. So plus or minus of the thing. So we will say, yeah, if it likes for you and everything settles between you and the real estate agent, you may buy that property. So this is how we understand the scatter plot. So what is plotted on the x-axis is this thing, square feet. On the y-axis is the house price. So let's try to do it in this thing. So we have already seen this thing, but this is done. We have to do it. So we get this. So as I told you, we get an equation for this thing. So we are Excel will not report this kind of equation, but the commercial softwares like SPSS, SysStat, SAS, Data, and all will report this thing. So house price, there's a caret symbol. And so house price predicted is equal to 98.24. That will be B0 plus 0.10. So is the coefficient, that is the B1 into square feet. So for any square feet, the real estate agent puts, you will get a house price. What's the data he had? So he used 10 records to create this equation. So this is what the linear regression does. This is how we have to understand. So this is the stepping stone to predictive analytics, which is a part of business analytics. So we will also solve it. So I should get this equation, same thing, somewhat. So on your laptop also, I have provided you the data. Let's try to do it. So go to data, click on data analysis. So say regression, it is already there. So input Y range. So this is my Y range. So this is my X range. So if it is more than 2x, you have 1x, you have it. So to copy 2 vectors. Okay. So labels, the headings I want. So confidence level is 95%. That's fine. Output range, so I have to mention it. I'll put it somewhere at E here. So you can ask for many plots and all. That's the fine. Now at this moment, we'll keep it as it is. If I say OK now, so this is the how it outputs it. Let me just increase the size of this. So who all got this thing? So this is what I got an answer to our problem. So what is of interest? So this one, R square T statistics P value. So the coefficient. This is where I tried to have my so standard error also will be important. So our equation was able to get 58% of the variation in the R. It was able to capture the information. So this shows that still about 42% of the information. So that is shown in the standard error. So this is what it indicates here. So regression as a whole looks fine to me. I have the equations, whatever is ready for me, perfectly right. So I have my p value. So and I have my confidence intervals. So this is something looks very linear and kind of a thing. We find that this is the best way which we can describe this data. Why I told you 42% of the data is missing. Maybe one of the cases is like maybe we need more data. One thing had just 10 records. So maybe the data record should go to 100 or 200. Or much more important than is like there should have been other X also. So I had only one X here, that was the square feet. Might be it should have information of, say, for example, whether how much bathrooms were there. So whether it has about, I don't know what I can say. It is a 3 BHK property or a 2 BHK property. That information is. So if you add this thing, so this thing may go up. So this may come down. So what is shown here is the error component. We are modeling a stochastic problem. Statistics, what is the error is very much important. It is not wrong. It is much more error. So somewhere the answer lies. So the explanatory variables, the predictors to this problem are there. So which we have to take notice of. So whenever you do the model as an analyst, you should be 100% sure to put the right variables, put the right data and all, prepare the data, subject it to analysis. So this is how a regression is done. So this is the error component. So error component means this epsilon, whatever we. In our problem, roughly about 42% of the information is still missing. So that is error. So I got 98 and also in Excel, it will not give you equation like this. We have to prepare it, put it. So as part of my this thing, I have put it. So whatever comes, we need to put it and we have to calculate the things. Okay. So I have this ready. What is there on my so I put a line of best fit to it. So the slope is 0.10 for that number. So that is how it's calculated. Intercept. So exactly you see that thing. So from 0 to 100, if you take it on the y-axis, so 98.28 is the place it exactly intercepts. So mathematics perfectly scientific way it matches. It is not some black box theory, magic, no magic and all in front of your eyes. Pure mathematics, how we calculate it. And it is a house prediction model, I can say. So real estate people will use it. It's are being used as I speak to you also. I think some of you might have gone for purchasing a property like a flat or a house or something like that. So people so some kind of per square feet they would have mentioned like 5,000 rupees, 6,000 rupees, and to calculate something and all. So all this thing behind the thing, this would have been the scientific. Only people who are very big builders or some very big real estate people and all will try to, not small time people. They just go by the street logic, not right. Of course, the same thing can be translated to any problem solving challenges, anything it might be, wherever you want to apply linear regression, you have to apply. You have to think in this. That is very much important. So what I showed there, yes, theoretically I showed this thing. Out of experience, people have built theoretically correct. That is what I did. Exactly numbers matches. Intercept you see. Bang on dot. So now we have to interpret. All done. Very good mathematics. Very good. We clap for mathematics and all. But yeah, interpretation is our forte. It's not that nobody will interpret for us. We have to interpret here. So I have got this equation. So B0 is the estimated average value of y when the value of x is 0. So I put square feet 0 there. So after plus sign that becomes 0. So 98.2 per is an average value. I mean to say, so house price is around a basic value. So whenever you go in area in which part of the city or something like that, you put a 0 and on an average, if you have taken data from that particular locality or something like that, the average price is 98 into 1000. So some $1,000 with the average price. That's how we should interpret. Because a house cannot have a square footage of 0, B0 has no practical implementation. Mathematically, it is correct, but a house cannot have square footage 0. We are not saying selling an empty space to anybody. That has no value. This is how our interpretation should go. How this practice will come, not one day, 1 week, 1 month, and all. Maybe it takes 1 or 2 years to articulate correctly. Would have done things perfectly, everything and all. Statistically, would have proved everything perfectly, but to interpret is the challenge. In examinations, usually you get these challenges. You have to put the data, or if you are given an equation like this, a snapshot of the data, how would you interpret will be a question. That's an academic exercise I'm talking about. So for example, if your client throws you some kind of a problems, you have to think in mind only. You have to build a framework of the data and how it will be, what you are going to all. That was about. Next thing important is like how to interpret B1. So B1 estimates the change in the average value of y as a result of a 1 unit increase in x. So that is how we should interpret. I mean to say here B1 is this 1.109, tells us the mean value of a house increases by 0.109 into 1000, that is about $109.77 on average for each additional 1 square foot of size. That is the scientific. So for your problem, say you are solving something in some retail, marketing, HR, or some engineering problem and all. So you have 1 y, 1 x and all. In the context of the problem, you should be able to interpret it. So what it tells is, I got that's a mathematical number there, 0.109. So I have to multiply, as I told you, this is in thousands of dollars. I multiply it. So if I multiply it, I get roughly about $110. So for a per square foot increase in the size of that particular apartment. So if an apartment size in this day will be 1530, so 1 square foot. So how a real estate person will negotiate with some might be a very odd apartment or something like that. So it might not, it might be 1535. So what he will do is he'll put that thing. So for $110 to 1535. So that is about, you can think, or he will also do that adjustment. So we'll put a $110 to this thing. He will get an answer to it. So say that for just about 1535 apartment space. So he is earning about, for the unit of 5, he will earn 110 into 5. So that will be roughly 11 5s are 55, 550 more dollars. So that's the interpretation which you have to make. You have to be careful, see what is there, correctly understand and do it. This is very simple. You had only one y, leave y will be there. Any simple linear, multiple linear will have only one y, and simple will have one x. So it becomes a complex when we say we have two x's, that becomes a multiple linear. So how to interpret using one x, one y? How do you bring the joint interpretation? Is left to the power of your interpretational skills. So what he has to do? I have this equation ready. How will the real estate fellow use it? The house price. So predict the price for a house with 2000 square feet. The question. So what I told you that the left of the equation is y hat, we call it. Here it is house price hat for an estimated house price or predicting the house price. So I have data of 8.25, 0.109 I have a square feet. I impute the value of 2000 there. I get 317.85, which I multiply with 1000. So roughly for a 2000 square feet apartment, so the price will be 307, I don't know, like $317,850, something like that. That's how we should be able to tell. This is where the actual negotiation starts. So let me pause here for a moment. Any doubt? Was I able to convey things to you properly? Any challenges you have? Or anything you wish to let me hear? Any questions?
No, sir. It's fine.
Yeah. Okay. So it can be any problem. So data can be 1 million records also, fine. Same logic works. If it is 10 records like this also it works. So if you have more access also, same logic works. But to understand this, we have taken one by one. So this is how we should interpret. A common example only I have chosen. No, nothing fancy here. So when using some caveats and those kind of things, and using a regression model for prediction, only predict within the relevant range of data. So relevant range is wherever the data is. So this might work. So relevant range, let me do that. I think the maximum number is 2450. The minimum number is 1100. So this works fairly good for square feet between 1100 to 2450, or it can be from 1000 square feet to 2500 square feet. This kind of logic work, data and all. We're not bothered about why it can work. So relevant data will be in that frame. Put a boundary wall to it. So that is very much important here. So I cannot use this for any data set has 800 square feet and about 3500 square feet kind of a thing. So my boundary condition is 1000 square feet to 2500 square feet is what I can play around the equation. So do not try to extrapolate beyond the range of observed. So this is something which we have to keep in mind. Of course, what all those things mean in terms of pure statistical things. SST is total sum of squares. SSR is regression sum of squares. SST is error sum of squares. So how do we calculate the SST? Y bar we have, yi is a observed value, yi hat is predicted value. So the same data only, you remember the managerial economics example, with that kind of a thing only, we're trying to predict. So what does it will say? Measures the variation of yi around the mean. Regression sums, explained variation, unexplained variation. So in terms of a theoretical thing, so what will be y bar in our equation? When I put after b1, if I put the value of x, I get a value of b0, then that is assumed to be the y bar line. So it's a theoretical construct. Okay, practically we don't do it, but theoretically we understand this. So y hat, the blue line is the line of best fit. So that is the y hat. So where will SSC come? The difference between the line of best fit to the blue line. Total sum of squares, SST, whatever it is, like from the blue line to the average line. From the blue line to the average line is SSR. So R square, I told you how much it was able to tell me the variation in the data. That is known as coefficient of determination, and its value will always lie between 0 and 1. So that is noted by R square. So it's calculated like SSR over SST, that value. So R square is equal to 1 when I say perfect linear relationships are determined like this when all the observed data falls on the line of best fit, we get R square is equal to 1. But it's a very, very, very rare condition we get this thing. I don't say weak, but if R square falls between 0 and 1, acceptable very much. So if you ask me, sir, what could be the R square value? So best rule of thumb, it is nothing scientific or something like that. So it should be something around 70 to 75% of the variation explanation is you have modeled the data perfectly. That's only a rule of thumb, that's all. So R square is equal to 0. Yes, you do get this kind of a thing in very rare circumstances. You have no relation. So where do you find these things? Here, as I already put that color on my Excel sheet, R square is this thing. So 58.08% of the variation in house prices is explained by variation in square feet. So to make that up to 70%, I need to add some more data. As I told you, number of bathrooms, number of rooms in the house or something like that. Might be that will boost. It is might be in quotes. So where did I find regression sum of squares, total sum of squares, all in the equation. So the same kind of output will come in R or any commercial softwares also. Some commercial softwares have put some additional business logic in there and they come up with very good output. One among them is like SPSS, SAS and all. They come up with very good output. So error is important, I told you. We got a very fancy formula for that thing. So 41% is something which I need to explore. Still, I'm not able to get that information from this data set. So how do we understand that thing? comparing standard errors, the magnitude of that whatever the SYX will always be judged relative to the size of Y values. So here SYX is $41.33 thousand is moderately small relative to house prices in 200 to 400 range. So that's what we can try to come up with standard error. This is the main gamut of getting to understanding the regression. So this is what I had for today's class. There's one more example with all the details given here. You can study solved for you. You can look at this also. So this is what I had for class. If you have any questions, I'll be happy to answer.
Sir, I appreciate your time and it was a great experience. Now we just need to learn, maybe practice again and again
Yes,
to get a hold of it.
please work on many things. As I told Survi, like anything you have apart from this thing also. So you complete a course and move on, go to different aspects in your career or whatever, it's fine. Do reach out to me if you have any challenges. So
Yes, sir, we may need to come back to you
Yeah.
sometimes for questions.
yeah, anything, please reach out. So at the best I try to help, because that's a promise which I gave to my professors who taught me. So it was not a professor from my university days or something like that. Many people have taught me many things. So you cannot always learn with anyone. So whoever taught me told me that you have to impart the knowledge. That's why I try to do it. So because we have learned that very hard way. So all these things were not there. I learned and all. Slowly computer evolution was there. When I started, of course, we coded this thing. As I told you, why my lectures will have all the fancy things about Newton Raphson and all. So yes, because that's the case. It was commercial softwares have slowly made an appearance, but not that much, because we didn't have, our university didn't have money to buy anything. So that was a challenge to be code. So we had a very fancy programming language known as Fortran. I don't know how many of you have exposed to it or remember those things and all. So yeah, Fortran stood for formula translation. So we didn't have any this 32-bit, 64-bit systems and all. We had what we call very fancy systems like XT and all. It had 2 drives. We had to boot the system in one drive, do things. All these things happened. So when I say like I was exposed to computers about 35 years back, that's the first time. So I'm also an alumni of Dayanand Sagar college, at least. Didn't have, at least as part of my undergraduate course, it didn't have. When I moved to my master's, this thing, they had this thing. Slowly, I also had exposure that. Now it's fine, fantastic. Okay, so we have no questions. Let me stop sharing here. So do get back to me without any hitch. Don't wait for anything and all.